Fick's first law should be rather called Fick's equation, as calling it a law would be rather a misnomer. That's because of the empirical nature of the law. Fick's law relates quantities in diffusion of components in a binary mixture, which could either be homogeneous or heterogeneous. Diffusion plays an important role in separation processes of homogeneous or heterogeneous mixtures, which are major operations in chemical process industries. These operations are called mass transfer operations. The mass transfer section has a variety of topics, starting with molecular diffusion in fluids. It ends with many variety of separation techniques for homogeneous as well as heterogeneous mixtures of solids, gases, liquids that frequently occur in chemical process industries. The syllabus is vast. So the basic and intermediate level of preparation for the GATE examination should actually focus on what has been asked previously. If we have an analysis of that, we can find in the past decade, there were average 12 marks questions, inclusive of 1 and 2 mark questions were out of this section. But earlier to that, 2003 to 2013, on an average 16 marks questions were out of this section. There is a change, but that should not discourage us. Instead, what we should focus is on what type of question and what are the frequently visited areas from this section by the GATE examination. What are the standard textbooks and references one can use for mass transfer? Mass transfer operations by Treble is the standard text for the subject. The other one, unit operations of chemical engineering by McCabe and Smith. I had used these two texts for my preparation of GATE examinations. But I have recently found out that the mass transfer by Binay K. Datta is a pretty much good text in that it offers plenty of multiple choice questions which we can practice based on the different topics that we learn. So this would be a good text to start off. The other is Transport Processes and Separation Process Principles by Gankopoulos. This is another text which is very well organized. It has plenty of solved problems, and we can use this text for your preparation. I will focus on two objectives in this session. First, I will elaborate the Fick's laws and their application through previous year questions on GATE examinations. Second, I will present an alternative derivation to the Fick's second law using probabilistic or stochastic framework, the Einstein derivation. The Fick's second law, also called diffusion equation, has widespread applications, and I will discuss a few. Let's start with a cup of tea, the jaggery tea. The solid jaggery is sitting at the bottom of the cup. If I don't stir the tea, then the jaggery is slowly diffusing. But why? Because it wants to get dissolved into the tea? Yes, the slow dissolution or diffusion of the jaggery is because of the concentration difference. You see, all of it is at the bottom of the cup. I can quickly mix it up and destroy the concentration differences, and I will get what I wanted, a nice jaggery tea. Why should I be bothered about the diffusion? Diffusion or mixing is a natural process. Things get mixed up. The challenges for a chemical engineer are separating those components of the mixture, which could be homogeneous or heterogeneous. And designing such operations requires finding the different rates at which components diffuse or mix up. The jaggery tea is such a multi-component mixture. That is, it has tea powder, jaggery, water, milk, etc. Separating these components based on their molecular basis is taken care by the biochemical engineering inside my body. I don't have to worry about it. And this is an example of solid diffusing into a liquid. Based on the state of the components that participate in the mixture, we could have liquid-liquid diffusion, gas-gas diffusion, the gas diffusing into other set of gases, gas-liquid diffusion, and gas-solid diffusion. Let's go. Let's define flux. The flux of a given physical quantity is the flow of the physical quantity per unit time, per unit area, where the area is perpendicular to the flow direction. Let's consider an example. Consider a round bottom flask partially filled with liquid A as shown. The vapors of liquid A will accumulate near the lower end of the tube and will diffuse upwards. At the open end of the tube, air is blown from left to the right at constant velocity. The vapors arriving at the open end are taken up by the air blown past it. So as soon as the liquid air vapors are swept away by the airflow, it is replaced by another set of vapors arriving from the bottom, thus establishing a constant concentration CAL at the open end. Similarly, a steady concentration of CS0 is established near the lower end of the tube. The diffusion is steady now. These concentrations do not change. Let's denote the diffusional flux by JA, where A symbolizes that it is the diffusion of component A. And as from the definition, the flux is the amount of the substance per unit area per unit time. Fick's first law states that the diffusional flux is directly proportional to the concentration difference and inversely proportional to the length over which this concentration difference is established. That length is L in the present case. Let's plug in a proportionality constant dAB, where AB signifies it's for diffusion of A into B. The negative sign further simplifies that the diffusion is against the concentration difference, is in the opposite direction of concentration difference. The other terms are as described. Ca0 is the concentration of A at the lower end of the tube. dAB is the diffusivity or diffusion coefficient of A into B. Cal is the concentration of A at the upper end. L is the length of the tube. The ratio of the concentration difference over the distance is called concentration gradients. That's pretty much Fick's first law. Before we move to a setup where we will define absolute and diffusional fluxes, let's review the definition of flux. The flux of a given physical quantity is defined as the flow of that physical quantity per unit time, per unit area, which is perpendicular to the flow direction. And there could be many more examples of such physical quantities. Mass flux, where the physical quantity is mass. Molar flux. Heat flux, where the physical quantity is energy flowing, measured in joules. Momentum flux, where the physical quantity is momentum, which is the product of mass into velocity. Diffusion is what's happening when there is no mixing. We just saw. But what if there is a mixing? To illustrate, we consider this setup. Here, cream-colored particles will label that as of component A, and the gray-colored particles that are of component B. So for these setups, let's set up the coordinate axis and a stationary observer at the origin. Let's identify the component A and B. As mentioned, the cream-colored particles are component A, and the gray ones are component B, and here is a region that is highlighted. We need to define an absolute molar flux. So this absolute molar flux measured in kilomole per meter square per second is the molar flux observed by a stationary observer sitting at the origin. In bulk movement or convective flow, as shown, a region or a portion of the fluid moves from one region to the another. This movement actually lifts with it some particles of component A and some particles of component B. So the portion of the fluid which moves from one region to the another, particles within, they get an easy lift to move from one region to another. This is the absolute flux denoted by N. And since the portion of the fluid actually carries with it component A and component B, so the total flux will be the sum of the individual fluxes of the components. On the other hand, we have seen the particles of component A will diffuse towards the right because we have lower concentration of component A on the right-hand side. So they will diffuse to the right. Similarly, component B has a lower concentration to the left, so they will diffuse on the left-hand side. This is called the diffusional flux. We have shown here the diffusional flux for component A, which is diffusing from left to the right. And that was our Fick's first law. So now we identified two fluxes. One is absolute with the stationary observer measuring it, and the second was diffusional flux due to diffusion. We now have identified for component A two fluxes. The first flux, which may be due to bulk motion or convection of the portion of a fluid. And the second is the diffusional flux. While the diffusional flux for the component A is solely that of component A, the absolute molar flux actually includes both the components. So we have to take a fraction of the bulk motion, which is component A. Simply we can write the flux of component A is made up of the bulk motion or convective flow and the diffusional flux of A. Let's play around with the units. Kilomoles of A per meter square per second, that's on the right hand side, that will be the flux of A, which we can rearrange sort of writing kilomoles of A per meter cube. This then becomes the concentration, and meter per second, this becomes the velocity. We still preserve the units of flux. That indicates that Na could be written as the concentration of A into the velocity of A. But what velocity? We'll come to that shortly. The total flux is kilomoles of A plus kilomoles of B that are flowing per unit area per unit time. And similarly, we too can write for it the total flux is the total concentration with the total velocity. So this velocity is sort of some average velocity. We'll see what it is. Substituting back in equation 1, I can get CAUA is equal to XA as its CU plus GA. Rearranging that, I can see that the diffusional flux is actually can be expressed in terms of the concentrations. The XA into C is in fact the concentration of A. Therefore, we can write the diffusional flux as the concentration of A multiplied by the relative velocity of A. The relative velocity is with respect to some average velocity, which we call as molar average velocity of the mixture. Fick's equation rather has different forms based on different velocities. We had seen UA, that was the velocity of component A, and U, which was some average velocity of the mixture we yet to define. It could be defined as the molar average velocity, U. And as we can see, it is the weighted average of the component velocities using the mole fraction, where C is the total concentration here, Ci will be the component concentration in the mixture. This is the molar concentration, and this is the velocity of that species with respect to a stationary observer. Similar to a weighted average velocity based on moles, we could have mass average velocity, which is based on the weight fraction or mass fraction. And since we're using mass fraction, we're talking here about the densities, the density of components and the total density of the mixture. There is yet another velocity, which is called volume average velocity, which would be just the volumetric flow rate divided by the cross-sectional area across which the volumetric flow rate is measured. That would be the volume average velocity. Corresponding to all this velocity, what are the respective Fick's equations? We will see in a while. Let's note down what we have learned about Fick's first law. The diffusional flux is proportional to the concentration gradient, the proportionality constant being the diffusivity or diffusion coefficient. This equation actually is based on the volume average velocity. So what's the difference? We have yet another flux, which here, for sake of simplicity, we're denoting with the same symbol for the flux, but which has the concentration of component A split up as the total concentration multiplied by the mole fraction. So this equation is based on the molar average velocity, where we know that the molar average velocity is the weighted average of the component velocity based on mole fraction. Similarly, we have another form of the same equation using the mass average velocity, where instead of concentration gradient, we have the gradient of the mass fraction of the components. That's how it is. So here is the flux based on molar average velocity. We know how we had derived this. We can write it in terms of the absolute flux, NA, of component A. The absolute flux is just the flux by taking into account the velocity of component A with respect to a stationary observer. That's the diffusion coefficient here. No, this is the concentration, this is the mole fraction, and this is the mass fraction of species A in the solution. Similarly, these are the velocities of species A and molar average velocity, U and U. The fluxes, JA, that's the diffusional flux. NA is the absolute flux. So the point to note here, the diffusional flux is with respect to a relative velocity. NA is with the velocity which is with respect to a stationary observer. Let's see some of the properties of diffusion coefficients. Consider a solution where the total concentration is constant, which is the sum of concentration of individual components. If we take the differential, we find dCA plus dCB will be equal to 0 because the concentration is constant, which gives us dCA is actually negative of dCB. So we have related the concentration of the two components. And if you look at the concentration gradients over the same distance, then concentration gradients being equal for the two components, their fluxes should also be equal, because according to the Fick's laws, the fluxes of the components are proportional to their concentration gradients. This implies that the diffusivity of A into B is equal to the diffusivity of B into A. This is an important result. This indicates that the diffusivity is actually the property of the mixture rather than the property of being component A or component B. Consider ideal gas mixture. For ideal gases, we have a very strong kinetic theory of gases, which implies that the diffusivity of the gas is proportional to the mean free path. The mean free path is the distance a molecule must go through before it bounces or collides with another molecule. Where does this mean free path and diffusivity come into picture? Mainly when we deal with porous catalysts, where the size of the pore compared to the mean free path actually categorizes the diffusion in two ways. Ordinary diffusion, if the pore size is way greater than the mean free path, so the molecules actually bump more often into other molecules of the same gas or other gas rather than with the walls of the pore. In case the pore diameter is small than the mean free path, then the molecules are bouncing off the pole walls more frequently. That is called Knudsen diffusion. What about self-diffusivity? Self-diffusivity refers to the mobility of the species in itself, such as the component A molecules diffusing among the A molecules. Pictorially, we can see how the reactants and products as they diffuse through the pore to the catalytic sites and come out. So as we can see, the pore diameter is actually a separating criteria for ordinary diffusion as well as Knudsen diffusion. Let's take up a question on diffusion coefficients. The diffusion coefficient of A diffusing into B is equal to the diffusion coefficient for B diffusing A. Both are equal for an ideal gas binary mixture. This indicates that the diffusion coefficient is dependent on the concentration or partial pressure. The second option, the diffusion coefficient is property of the binary gas mixture. The diffusion coefficient is independent of mean free path. The diffusion coefficient is independent of the temperature. All they look sort of confusing. So let's try to eliminate one of them. The first, the diffusion coefficient is dependent on concentration or partial pressures. In this situation, if the diffusion coefficient is dependent on the concentration, then we know that the Fick's law changes itself, because it's not only then proportional directly to the concentration gradient, but it will also depend upon the diffusion coefficient, which is not the case. So clearly option A is incorrect. Diffusion coefficient is property of the binary mixture. So this is more generics, and just leave it for now and evaluate others. The diffusion coefficient is independent of mean free path. No, we know that for ideal gas binary mixtures just discussed that the diffusion coefficient is in fact directly proportional to the mean free path. So C is incorrect. The diffusion coefficient is independent of the temperature. Well, we know this as well is incorrect, because the diffusion coefficient we have or we can derive from the ideal gas law, and which is a function of temperature. So diffusion coefficient is not independent of temperature. So this leaves us with only one option. The diffusion coefficient is property of the binary mixture. Let's take another question. If the diffusional flux for component A in a binary mixture is written as JA is equal to CA multiplied by VD. So this is a new stuff here, where VD is the diffusion velocity and C is the molar concentration. Then we have seen the expression for JA in terms of CA. So let's see what are the options. The diffusion velocity is with respect to stationary frame of reference. The diffusion velocity is relative velocity of component A with respect to velocity of component B in the mixture. The third option, the diffusion velocity is relative velocity with respect to the mass average velocity of the mixture, and the diffusion velocity is relative velocity with respect to molar average velocity of the mixture. The diffusion velocity is with respect to stationary frame of reference is incorrect. We know this because if you look at the expression, JA was equal to CA in bracket UA minus U. We have discussed that. So VD is just representing UA minus U, and that is a relative velocity. So the first option is incorrect. Now, is this relative velocity of the component with respect to velocity of component B? No. Whether it is a relative velocity with respect to average velocity, yes, but this is mass average velocity. And we see in the expression, this is the molar concentration. So definitely the option D, which is the diffusion velocity is with relative velocity with respect to molar average velocity of the mixture, is the correct one. Let's consider some of the examples on the Fick's first law. It's worthwhile to know the diffusivity rather in the order of magnitude. For the gases diffusing, it's of the order of 10 raised to minus 5 with the units meter square per second. In liquids, it's of the order of 10 raised to minus 9 meter square per second. So the diffusivity of the gases is higher than that of liquid, the first point to note. There was a question in 2003 GATE examination for 1 mark, which was regarding the order of magnitude. The diffusion coefficients in meter square per second of acetic acid in benzene, that's liquid in liquid, is, and the options were these 4. If you look at the options, the orders of magnitude are quite different among all the 4 options. So this information, order of the magnitude, could easily help us spot that the correct answer is C. The liquid diffusivities are of the order of 10 raised to minus 9 meters square per second. The order of magnitude of diffusivity had yet another question in GATE 2005 for 1 mark. In this case, they were interested to know the ratio of diffusion coefficient of gases to that of liquid and what's its order. The options were these 4. Looking carefully, if we take the diffusion coefficient of gas, which is 10 raised to minus 5, and that to that of liquid, 10 raised to minus 9, and if you look at the ratio, it will be somewhere around 10 raised to 4. 10 raised to 4 is pretty much close to 10 raised to 5. Therefore, the correct option is A. There could be different cases of flux. If the flux is time dependent, that's unsteady state. If it doesn't depend on time, that's a steady state flux. And the total flux is always sum of the component fluxes, as we already seen. Consider case 1, in which we have steady diffusion of A through non-diffusing B. An example would be gas absorption. For example, a gaseous mixture has ammonia as one of the components, and the single component ammonia is absorbed in water. So that's the case 1 example. Let's take case 2. This is a steady state equimolar counter diffusion. The direction of diffusion of components A and B are opposite to each other. That's what exactly happens in distillation, the rising vapors and the condensing liquid. The third case is of non-equimolar counter diffusion. So counter diffusion still holds, but the amounts that are diffusing in opposite directions to each other are not the same. For example, in catalytic reactions, reactants and products, they diffuse to and from the solid catalytic surface. Let's see an example more clearly. Here in the diagram, I have shown the solid catalyst as a sphere with a single pore in it. The reactants move through the pore onto the catalytic site and the products move out. So if we focus on the opening of the pore and we focus on that plane, we could see if the reaction is case 2, in which A decomposes into B. So the number of moles of A that are entering into the pore and the number of moles of B that are coming out, they're exactly same, and it is counter diffusion. That would be the case 2. In case 3, as we can see, 1 mole of A is moving inside the pore to the catalytic site, and when the products come out, there is 2 moles of the product. So it is non-equimolar. The number of moles of B is twice that of moles of A. That is the case number 3. There was a question in GATE examination in year 2003 for 1 mark based on the different fluxes. Component A is diffusing in a medium B. The flux Na relative to a stationary point is equal to the flux due to molecular diffusion if, and these were the options, mass transfer is accompanied by a reaction, diffusion of A is in stagnant medium B, molecular mean free path is high, and there is equimolar counter diffusion. Let's take a minute to think this through. The question says the flux of component A relative to a stationary point is equal to the flux due to molecular diffusion. We know there are two fluxes, and the flux of component A is equal to its molecular diffusion flux, the diffusional flux, the JA. So let's see. We have Na is equal to JA. That is what we should read from this clue. But the original equation Na is XA plus JA, where XANA is the fraction of the bulk flow, that is component A. We need that to be 0. For it to be 0, we can see Na should be equal to minus Nb. And the answer is D, which is equimolar counter diffusion. Because in equimolar counter diffusion only, we will have this term going 0. And if this term goes 0, then we have flux of A equal to its diffusional flux. You can readily visualize the plane across which there is equimolar counter diffusion. Let's initiate investigation of time-varying or unsteady state diffusion by setting up a mass balance equation across a small volume element in which we consider the flux variation only in the z direction. The incoming flux is here on the left-hand side. The outgoing flux similarly here coming out of this right plane. The area of the plane is delta x into delta y, which is the plane perpendicular to the direction of flow. Some of the symbols that we will use: M for molecular weight, T for time, Ca is molar concentration, and this is mass density as usual for a chemical engineer. Setting up the mass balance, we can see on the left-hand side, we have density multiplied by volume, that's the mass over time. So dimensionally, on the left-hand side, we have mass divided by time. Similarly, the dimensional consistency is maintained on the right-hand side. We have the flux, which are the number of moles per unit area per unit time. To account for the area, we have delta y into delta x, and the moles to kgs we convert using the molecular weight. So this is dimensionally consistent, and it also has mass over time as the dimension. Similarly for this term as well. The rate of generation we take as 0. That means no chemical reaction for A inside this volume element. This is just to keep the things simple. Dividing throughout by the volume element, we see that only delta Z is there on the right-hand side. Further, we can write the mass density of A in terms of its molar concentration using the molecular weight, which ultimately cancels then on the left and right-hand side. And if we limit delta Z to 0, we get this partial differential equation, which connects the concentration variation with respect to time to the molar flux variation across the distance. Rather than following the lengthy derivation given in Treble's book, which actually takes all 3 dimensions as well as the bulk flow into account, we can use a small trick to arrive at the same result quickly. Remember, in the previous example that was from the GATE examination, we have seen the equimolar counter diffusion has a simplifying expression in which the molar flux of A with respect to a stationary observer is its diffusional flux. This is what I mean. This is the flux of A with respect to a stationary observer, which is actually diffusional flux in case of equimolar counter diffusion. And the diffusional flux is pretty much given by the Fick's first law. Let's use the equimolar counter diffusion, in which we have the flux with respect to a stationary observer is the same as the diffusional flux, to simplify the differential equation. So if we plug in the diffusional flux into equation A, equation 1 for Na, we can see that it's just some of the manipulations, and we can find ultimately on the right hand side we get the second derivative of concentration with respect to distance. So we have del Ca over dt, the time variation in concentration of A, the temporal variation on the left hand side, connected to the spatial variation across the z direction in the present case of concentration. Similarly, we can add similar terms which are for the x direction as well as the y direction. So effectively, with the Fick's second law, we can have the concentration dependent upon four variables: t, the temporal variable; x, y, z, the three spatial directions. So in turn, Fick's second law covers the unsteady state diffusion. Since transport phenomena deals with many different types of diffusivities, let's have a look at the equations. The Fick's second law, here we have the diffusion coefficient, the molecular diffusivity. The diffusion of energy, heat, we have the thermal diffusivity. Diffusion of momentum, we have the momentum diffusivity. The exact expression for thermal diffusivity in terms of the thermal conductivity K, the specific heat, and the density. Kinematic viscosity, which is also the momentum diffusivity, is the ratio of absolute viscosity divided by the density. In the next session, we will see the derivation of these expressions. The diffusion equation is widespread and shows up in numerous fields of investigation. For a chemical engineering and transport phenomena, we have the mass diffusion, the momentum diffusion, the heat diffusion. All of these diffusions are based on molecular or particulate nature of the underlying substances. But that's not the case if the diffusion equation has to be applied to the other fields. For example, in option pricing and financial mathematics, the Black-Scholes equation has the diffusion of stock prices. The stock prices has no molecular or particulate basis. Similarly, in population genetics, it is the genetic variation that is diffusing throughout the population. Nerve impulses, the Hodgkin-Huxley equation in neuroscience. The predator-prey interaction in ecology. So the diffusion equation in its multiple forms shows the underlying entity which is diffusing. So we'll restrict ourselves to the transport phenomena, and in another set of sessions to the option pricing and the Black-Scholes equation. So far, we have seen Fick's first law and the diffusion coefficient or diffusivity that shows up as a proportionality constant in the Fick's first law. We have also seen different types of fluxes and velocities and their application through various examples. Is diffusion coefficient only a proportionality constant? That's all there to it, to the diffusion coefficient. The diffusion coefficient actually represents the random motion of molecules or particles. It's not indeed only a proportionality constant. Say for self-diffusivity, that's the measure of mobility of a species. Say for example, water at room temperature. It's the water molecule that are diffusing through the surrounding water molecules. So self-diffusivity has a meaning, the measure of mobility of that species. Molecules, particles, these are tangible things. The random behavior is shown by other entities as well, like a stock price. What do we do in that case? We take out the random motion as the key ingredient of diffusion coefficient, and we understand that The random behavior, also called stochastic behavior, which we can model using probability models, is actually going to be the true representation of diffusion coefficient. That's it. The probabilistic models for diffusion coefficient is not part of the GATE examination and its syllabus. If you want, you may skip and stop here, or you could jump on for a fantastic ride where we will show the Einstein's derivation for diffusion coefficient. The diffusion coefficient represents the random motion of the underlying particles in a given binary mixture. Let's pick displacement, our key ingredient for modeling the random behavior that is in diffusion coefficient. We pick the displacement axis and a small interval d delta on the displacement axis. We could then count the number of particles with the displacement delta, the number of particles with the displacement delta plus d delta. Let's say, for a simplicity, those particles count to 4. There could be total number of particles in the system as well. So what is the fraction of these particles with displacement delta and delta plus d delta represent? They represent a probability, sort of probability. And this probability we can compute for each infinitesimal interval on the displacement axis, like this. We can rearrange this to find the number of particles out of the total particles that has displacement between delta and d delta. That's our probability density function. To our probability density functions, let's add 2 simplifying things. First, that the probability density function does not depend on time. It does not change with time. So the fraction of particles in a given displacement interval stays constant throughout the time. The function, probability density function, is symmetric. So it doesn't differentiate between the positive and the negative displacement. The fraction stays the same. The distribution function will most likely look like the normal distribution function, where we can see the majority of the fraction of the particles has a 0 displacement to maintain their mean position. To this setup, we will add one more ingredient. That is, we focus on a small volume where we define rho n as the number of particles in unit volume at a given location x at a given time t. We now have the probability density function, and using that we can find the number of particles that fall within an infinitesimal interval d delta on the displacement axis. We can use this information to actually find the change in the number of particles by summing over all the displacements. Let's see how we can do this. The number of particles in a given volume V changes from the initial time, which is 0, to a time t, because of the random motion of the particles that enter into the particular volume and they leave from the particular volume. All those variations could be accommodated if we sum over all displacements d delta. If we sum over all displacement, we effectively get the configurational changes in the particle, that is, the particles that enter or leave. Hence, we can find the particle in a given volume at any given time t. Let's be more concrete. Consider the volume element as shown and some particles outside the box, some inside, some outside here. This we label as our particle density at a given location x and at a given time t. As particles enter and leave this box due to the random nature of the motion, the density is going to change after an infinitesimal time dt. How we can account for these changes? The number of particles which we can obtain by multiplying the number density by the volume element, these are the number of particles after t plus dt. They should be proportional to what were the initial particles at x and t in that volume, and if we sum over all the displacements, because through the displacements we can keep account of the number of particles that enter and leave. Expanding on this, we can in fact write it in a form of an integral where we use the probability density function, integrate over all displacements from minus infinity to plus infinity. So this is going to give us the changes in the number of particles in the given volume dV. Let's take it from the equation we have just set up. The number density of particles at some time later, dt, into the volume dV. This is the new set of particles in the box. Those particles we can also obtain if we sum over all the possible displacements and using the probability density function, so that we know what particles have left, what particles have entered into the box of volume dV. We can expand the dV into its infinitesimal elements, dx, dy, dz, along the coordinate axis. But anyway, the volume elements will cancel out on both sides. What we have now is the number density as a function of time given in terms of the probability density and summation over all displacements. The savior here would be using a Taylor series expansion. Using Taylor series expansion on both sides, we can expand on the left-hand side the number density in terms of temporal variable t to the first order dt. On the right-hand side, we expand the number density using Taylor expansion to the second order in displacement. We can separate out these terms and investigate them one by one. The number density doesn't depend in any way on the displacement. So this will come out of the integration, and this is like an even function. This will survive. The delta, however, here is an odd function, and the rest of it is an even function. Odd into an even function, an integration minus infinity to plus infinity. This would be an odd function and it would cancel out. Here we have an even function inside the integrals. This will stay. We now have only two terms left on the right-hand side. Nothing changed on the left-hand side. We can take out the parts that are not function of delta outside the integration. Looking at this first term on the right-hand side, integration minus infinity to plus infinity p delta d delta, we could rewrite in terms of the number fraction dn by n. If we integrate the number of particles and divide them by the total number of particles, we know this ought to go to 1. So this integral evaluates to be 1. We can see that there is this number density at time t term similar to this number density at time t on the left-hand side. These two will cancel out. Now what we will left with is the first order term in time and the second order term in the displacement. We need only just to rearrange these terms now. A little rearrangement where we can have the dt term sent out on the right-hand side and the integral clubbed into a constant d. We can see that that's our expression for diffusion coefficient. If we compare this equation to the diffusion equation, that is some sort of time average of the squared displacement using the probability distribution we have assumed for the displacement. Let's summarize the equation just derived, where we have the number density dependent on time as well as the spatial direction, x. The diffusion coefficient now has a concrete expression in terms of the probability density function for the displacement of the particles, and it is time averaged. What we can label this D as the diffusion coefficient or diffusivity. We can see the probabilistic frameworks or model behind the diffusion coefficient now. This is the approximate version of the derivation used by Einstein, but this is not the exact one, but the reasoning is along the same lines. For this derivation, we have been considering a box of volume delta V and the particles coming into the box, leaving the box because of the random motion. What we have here then is an expression of self-diffusivity. But that doesn't stop us from extending the application of this probabilistic frameworks to a mixture of two components, component A, component B of the binary mixture, approximately the Chagrin and the T as component A and component B of the mixture. We have seen through the derivation for diffusion coefficient on the basis of probabilistic modeling of the displacement. Let's summarize. Diffusion coefficient has a stochastic basis. It's no longer a proportionality constant. Since the diffusion equation appears in various fields, if we have solution for one particular field, we can extend it to others. We're just going to see the two applications of it. In finance, for the solution of Black-Scholes equation, while in chemical engineering, we are going to take it like a bit far into mass transfer chemical reactions transport phenomena. So that's it for today's session. We will continue the chemical engineering, GATE previous year questions, mass transfer, and other sections on the syllabus in the subsequent lectures. Thank you. If you have any questions, you need more info, you can contact me at info.quanta.learning@gmail.com. Time for yet another cup of tea. Thank you guys. Bye.